The void is disappearing. Let me be precise about what that sentence means, because it is pointing at something real and specific in contemporary theoretical physics and observational cosmology, not at a catastrophe unfolding on any timescale relevant to human civilization or to any civilization conceivable within the current epoch of the universe. But the specific things it is pointing at, the specific recent theoretical results, the specific observational evidence for the large-scale evolution of cosmic voids, and the specific Higgs field measurements that have generated the most sustained and most technically sophisticated discussion of vacuum stability in the history of particle physics are genuinely extraordinary. They change how we understand what empty space actually is, what its specific future might be, and why the specific distinction between empty and full is far more subtle and far more consequential than everyday experience suggests. Let me start with what empty space actually is, because this is the specific place where the story begins and where the most important misunderstanding typically occurs. Empty space is not empty. This is not a metaphor or a loose use of language. It is the specific, experimentally confirmed, quantum mechanically grounded fact that the vacuum, the specific lowest energy state of quantum fields, is not a featureless void. It is a specific, dynamically active quantum state in which virtual particles continuously appear and disappear. Quantum fields fluctuate around their specific vacuum expectation values, and the specific energy density of the vacuum is not zero, but takes a specific non-zero value that is among the most important and most poorly understood quantities in all of physics. The specific experimental confirmation of vacuum activity comes from multiple directions. The Casimir effect, the specific attractive force between two uncharged conducting plates placed very close together in vacuum, is produced by the specific modification of the quantum vacuum fluctuations between the plates compared to outside them. The force has been measured with specific precision in multiple experiments and matches the specific theoretical prediction exactly. The Lamb shift, the specific small difference in energy between the 2s and 2p energy levels of hydrogen that classical atomic physics predicts to be zero, arises from the specific interaction of the hydrogen electron with the vacuum fluctuations of the electromagnetic field. It has been measured with extraordinary precision and matches quantum electrodynamics calculations exactly. The vacuum is active. It has specific energy. And that specific energy, the specific vacuum energy of the universe, is one of the two specific quantities that the cosmological constant problem and the dark energy problem are about. The vacuum is not disappearing in the sense of becoming less active. It is potentially unstable in a specific, technically precise, scientifically important sense that requires careful explanation. Let me take you to the specific physics, the specific concept of vacuum stability that is at the heart of the space is slowly dying story. Quantum field theory describes the fundamental particles and forces of nature in terms of specific quantum fields, mathematical objects defined at every point in space and time, whose specific quantum states encode the presence or absence of specific particles and the specific energy of the vacuum. Each fundamental field has a specific potential energy function, the specific relationship between the field's value and its energy that determines both the specific vacuum state of the field and the specific properties of the particles it describes. The simplest quantum field theories have specific potential energy functions with a single minimum, a specific lowest energy state that the field naturally settles into. This specific state is the vacuum. It is stable in the specific sense that small perturbations cause the field to oscillate around the minimum and return to it like a ball at the bottom of a bowl. But more complex field theories, including the specific theory that describes the Higgs field, can have potential energy functions with more complicated structures. The specific Higgs potential, the specific mathematical function that describes the Higgs field's energy as a function of its value, has a specific shape that current measurements suggest may be more complex than the simplest, stable form. The specific relevant concept is metastability. A metastable vacuum is a specific local minimum of the potential energy, a specific state in which the field is at a local lowest energy configuration, but not at the absolute lowest energy configuration. The field is stuck in a specific local minimum, a bowl within a bowl, separated from the specific true minimum by a specific energy barrier. The specific analogy is a ball resting in a small hollow near the rim of a larger bowl. The ball is at a local minimum. It doesn't immediately roll away. But the global minimum is at the bottom of the larger bowl. Given specific perturbations, specific quantum fluctuations, the ball can tunnel through the barrier and roll down to the true minimum. If the electroweak vacuum, the specific current state of the Higgs field throughout the universe, is metastable rather than absolutely stable, the universe is in this specific condition, sitting in a local minimum, stable against small perturbations, but potentially vulnerable to specific quantum fluctuations that could tunnel through the specific energy barrier to the specific true minimum. The specific process by which this would occur is called vacuum decay. Let me now take you to the specific Higgs field measurements that have made the vacuum stability question one of the most actively discussed topics in theoretical particle physics. Because these measurements are specific, real, and their specific implications are genuinely extraordinary. The Higgs boson was discovered at the Large Hadron Collider in 2012, confirming the specific existence of the Higgs field and allowing the specific measurement of its mass. The Higgs boson mass, approximately 125.1 GeV, was not predicted by the standard model of particle physics, but is a specific input to it. And the specific value of 125.1 GeV has a specific consequence for the shape of the Higgs potential that was not anticipated when the measurement was made. This specific calculation, performed by multiple groups using the specific tools of quantum field theory and the specific measured values of the Higgs mass, the top quark mass, and the strong coupling constant, gives the following result. The Higgs potential evolved to high energies using the specific renormalization group equations that govern how quantum field parameters change with energy scale, develops a specific second minimum at an extraordinarily high energy scale, approximately 10 to 1012 GeV, that is lower than the current vacuum energy. The specific current electroweak vacuum, the specific state of the Higgs field at its current vacuum expectation value of approximately 246 GeV, appears to be a local minimum, not the global minimum, of the full Higgs potential. There is a specific deeper minimum at higher field values. The universe is, according to this specific calculation, in a metastable state. This is not a fringe result. It is a specific, peer-reviewed, widely discussed conclusion drawn from the best available measurements of the standard model parameters. The specific 2012 paper by Degrassi and colleagues, and the subsequent more precise calculations by Battazzo and collaborators in 2013, established that the current best values of the Higgs mass and top quark mass place the electroweak vacuum in the specific metastable regime, not in the stable regime where the current vacuum is the absolute minimum, and not in the unstable regime where it would decay immediately. Metastable, specifically, calculably, technically metastable. Let me now be specific about what vacuum decay would actually mean and why. Despite the dramatic framing, it is not something to be concerned about on any humanly relevant timescale. If the electroweak vacuum decays, the process begins at a specific point in space, the specific quantum fluctuation that tunnels through the barrier, does so at a specific location. Once the decay begins, a specific bubble of the true vacuum forms a specific expanding region within which the Higgs field has settled to its true minimum value. The boundary of this bubble, the specific domain wall separating the true vacuum interior from the false vacuum exterior, expands outward at the speed of light. Inside the bubble, the specific laws of physics are different from outside. The specific vacuum expectation value of the Higgs field is different, which means the specific masses of all fundamental particles are different, which means the specific binding energies of atomic nuclei are different, which means the specific chemistry of matter is fundamentally different. The specific interior of the bubble is not a place where atoms as we know them can exist. The specific physical constants that govern atomic structure would be dramatically altered. The specific bubble wall, expanding at the speed of light, cannot be preceded by any warning signal. Nothing can travel faster than the speed of light. If a bubble of true vacuum formed at a specific point 10 light years away, you would have no warning of its existence until the specific moment it reached Earth, and at that moment, the specific alteration of the physical constants would be instantaneous and complete. This is the specific space-dying scenario in its most dramatic form. Not gradual, not escapable, not reversible. A specific expanding bubble of altered physics, silent and invisible, expanding at the speed of light. But here is the specific and critical quantitative fact that transforms this from existential nightmare to theoretical curiosity. The specific rate of vacuum decay, the specific probability per unit time, per unit volume, that a quantum fluctuation tunnels through the specific energy barrier depends exponentially on the specific height and width of the barrier. And for the specific electroweak vacuum, with the specific Higgs mass of 125.1 GeV and the specific top quark mass of approximately 173 GeV, the specific calculated decay rate gives a specific tunneling time that is dramatically longer than the current age of the universe. The specific calculation gives a vacuum lifetime of approximately 10,400 years, or in some calculations, even longer. The universe is currently approximately 1.4 times 10 years old. The specific vacuum lifetime is 10,390 times longer than the current age of the universe. The void is disappearing on a specific time scale so long that it makes the heat death of the universe at approximately 10,100 years look like an imminent emergency. This is not a current threat. It is a specific calculated theoretical property of the specific vacuum state that the universe currently inhabits, a property that tells us something important about the structure of the Higgs potential and the specific status of the electroweak symmetry. Breaking that underlies all of the chemistry and physics we know. Let me now take you to the specific, most recent theoretical development that has changed how physicists think about vacuum decay and the long-term fate of the universe, the specific 2023 results that extended Hawking's black hole evaporation calculation to the universe's cosmological horizon. Stephen Hawking's 1974 result, Hawking radiation from black holes established that quantum effects near event horizons produce specific thermal radiation causing black holes to slowly lose mass and eventually evaporate. We've discussed this extensively in the black hole information paradox conversations. In 2023, a specific collaboration of physicists Heine Falke, Michael Dries, and Walter van Zwijlekom at Radboud University in the Netherlands, published in the Journal of Cosmology and Astroparticle Physics, applied the specific mathematical machinery of Hawking radiation to a different but formally analogous situation. Not a black hole horizon, but the specific cosmological horizon of the de Sitter universe, the specific boundary beyond which the accelerating expansion of the universe means that nothing can ever reach us or send signals to us, the specific argument is elegant. A black hole has a specific event horizon, a boundary from within which nothing can escape. This horizon has a specific temperature given by the Hawking formula and produces specific thermal radiation. The cosmological horizon of a de Sitter universe, the specific distance beyond which the expansion is fast enough that light cannot reach us, is formally similar. It has a specific area, a specific temperature given by an analogous formula, and should produce specific thermal radiation by the same mechanism. The specific result, the cosmological horizon radiates. Everything that exists within the observable universe, every particle, every black hole, every galaxy, is slowly, extremely slowly evaporating through this cosmological Hawking radiation. Not into nothing, into specific thermal radiation at the specific de Sitter temperature, approximately 10, negative 30 Kelvin, an extraordinarily cold temperature that makes the cosmic microwave background's 2.7 Kelvin seem scorching. The specific evaporation timescale for various objects was calculated by the Rodbaud team and is extraordinary. A stellar mass black hole of 3 solar masses, the smallest black holes produced by stellar collapse, has a specific Hawking evaporation time from standard black hole Hawking radiation of approximately 1074 years. But through the specific cosmological Hawking radiation mechanism, the same object evaporates on a time scale of approximately 1085 years. The specific most relevant calculation for the space is dying framing is the evaporation of the objects that we would expect to be the last survivors in the far future of the universe, the specific white dwarfs, neutron stars, and eventually black holes that will remain when the last stars have burned out. Each of these has a specific evaporation time through the cosmological Hawking radiation mechanism that is finite, extremely large numbers with exponents in the hundreds, but finite. The void is disappearing in the specific sense that even the specific quantum vacuum of the universe is radiating, however slowly, and everything embedded in it will eventually dissolve into the specific thermal equilibrium of the de Sitter universe. Let me now take you to the specific observational evidence that gives the space itself is slowly dying, framing its most directly measurable content, the specific evolution of cosmic voids that has been measured in the most recent large-scale structure surveys. Cosmic voids are the specific regions of the universe that contain very little matter, specific underdensities in the cosmic web, the specific gaps between the filaments and walls of the large-scale structure that contain most of the universe's galaxies. They range in size from specific tens to specific hundreds of megaparsecs across, and they occupy the specific majority of the universe's volume. Most of space, by volume, is void. The specific voids are not static. They are growing. In an expanding universe dominated by dark energy, the specific current epoch of the universe's evolution, the specific underdense regions of the cosmic web expand faster than the average, while the specific overdense regions grow denser as matter flows toward them along the specific filaments. The specific voids grow larger as their specific boundaries sweep outward and the specific interior matter drains toward the surrounding walls and filaments. The specific observational measurement of void evolution, how specific voids change in size, shape, and internal density over cosmic time, is one of the most powerful probes of dark energy currently available. The specific rate at which voids grow depends on the specific equation of state of dark energy, on whether dark energy is a cosmological constant with a specific equation of state of -1, or a dynamical field with a different specific equation of state. The specific reason void evolution is such a sensitive probe is the specific Alcock-Pachinski effect, the specific distortion of the specific apparent shapes of voids caused by the specific mismatch between the specific assumed cosmology used to convert redshifts to distances and the specific true cosmology. If the specific assumed cosmology is wrong, specific spherical voids will appear, specific, elongated, or flattened. By requiring that the specific statistical distribution of void shapes be consistent with the specific expectation spherically symmetric voids on average, the specific cosmological parameters, including the specific dark energy equation of state, can be constrained. The specific DESI survey, whose specific first-year results we discussed in the dark matter conversation in the context of the dark energy equation of state evolution, has produced the specific most comprehensive void catalog ever assembled. The specific DESI void catalog, published in 2024, contains specific hundreds of thousands of cosmic voids identified in the specific galaxy distribution mapped by DESI across specific billions of light years of cosmic history. The specific most important result from the DESI void analysis is consistent with and strengthens the specific overall DESI dark energy finding. The specific dark energy equation of state appears to be evolving, not the specific constant -1 of a cosmological constant, but a specific time-varying function that is changing as the universe ages. If dark energy is evolving, if its specific equation of state is changing, then the specific rate at which cosmic voids grow is also changing. The specific future of cosmic voids, their specific ultimate size, the specific degree to which they empty of matter, the specific rate at which the universe's structure becomes more and more concentrated in specific dense regions while the voids become more and more empty, depends on the specific future evolution of dark energy. The specific, most dramatic possibility consistent with some of the specific DESI dark energy evolution measurements is a dark energy that evolves toward a specific equation of state above -1, a regime called phantom dark energy, in which the specific dark energy density increases rather than decreases over time. Phantom dark energy produces a specific future in which the expansion of the universe accelerates without bound, the specific Big Rip scenario in which the specific accelerating expansion eventually tears apart galaxies, then solar systems, then individual stars, then planets, then eventually atoms themselves. The void is disappearing in this specific scenario in the specific sense that the specific voids between structures are expanding so rapidly that the specific structures themselves are eventually torn apart and join the void. Let me now tell you about the specific scientific debates surrounding the vacuum stability question, because the specific conclusion that the electroweak vacuum is metastable while robust has specific uncertainties that deserve honest treatment. The specific calculation of vacuum stability depends critically on the specific measured values of the Higgs mass and the top quark mass. The specific top quark mass is particularly important because it enters the specific renormalization group equations that determine the specific high energy behavior of the Higgs potential, and it enters with a specific fourth power dependence that makes the calculation very sensitive to the top mass value. The current best measurement of the top quark mass from the specific Tevatron and LHC experiments gives a value of approximately 172.5 to 173.5 GeV, depending on the specific measurement method used. The specific different measurement methods, direct reconstruction, indirect extraction from cross-section measurements, give specific, slightly different values with specific theoretical uncertainties about which method most directly corresponds to the specific theoretically defined top mass. The specific relevance for vacuum stability is that a slightly different top quark mass places the electroweak vacuum in a qualitatively different regime. A top quark mass lower by approximately 1 to 2 GeV would place the vacuum in the specific stable regime where the current vacuum is the absolute minimum of the Higgs potential. A top quark mass higher by a comparable amount would place it in the specific unstable regime where the vacuum would decay much faster. The specific current measurement places the electroweak vacuum in the specific metastable regime but close to the boundary between metastability and stability. Small improvements in the specific top mass measurement could shift the specific conclusion. This specific sensitivity, the specific dependence of the qualitative stability conclusion on the specific precision of the top quark mass measurement is one of the specific scientific reasons that the next generation of particle physics experiments is so important. The specific future circular collider, the specific proposed successor to the LHC at CERN, would measure the top quark mass with specific precision sufficient to definitively determine the specific stability regime of the electroweak vacuum. Let me close this first part with something that honestly captures the specific scientific significance of the space is slowly dying story, not as catastrophism, but as a specific, profound, experimentally motivated insight into the nature of the quantum vacuum. The specific calculation that places the electroweak vacuum in the metastable regime is not just a specific theoretical exercise about the far future. It is a specific, experimentally grounded probe of the specific structure of the Higgs potential at energies that no accelerator has directly accessed energies of 10 to 10, 12 GeV, far above the LHC's specific 13 to 14 TeV. By measuring the specific Higgs and top quark masses at accessible energies and running the specific renormalization group equations to high energies, physicists are effectively making specific predictions about the specific structure of the theory at energies that will never be directly testable. The specific finding metastability is a specific signature that the specific standard model extrapolated to high energies is telling us something specific about the specific physics that must exist at those energies. A specific, perfectly stable vacuum would tell us one specific thing about the high energy completion of the standard model. The specific metastable result tells us a different specific thing, that the specific physics above the specific scale of metastability is specific and important. Many specific extensions of the standard model specific supersymmetric theories, specific Higgs sector extensions, predict specific additional contributions to the Higgs potential that would shift the specific vacuum stability boundary. The specific constraint that the measured Higgs and top quark masses give metastability rather than stability rules out specific classes of beyond standard model theories that would predict a different specific regime. The void is disappearing. Not today, not in any epoch relevant to any form of life or complexity that has yet existed or could exist on any reasonable future timeline. But in a specific, calculable, theoretically grounded sense, the specific quantum vacuum we inhabit is not the specific final state of the universe. There is a specific deeper minimum. The specific current state is a specific local equilibrium, not the specific absolute ground state. And the specific long-term future of the universe on timescales that dwarf even the heat death involves the specific eventual transition to that deeper minimum. This is the specific scientific content of space is slowly dying, not a dramatic immediate threat. A specific, profound, theoretically grounded insight into the specific nature of what we call empty space and what its specific long-term fate might be. In part 2, I want to go deeper into what the specific big rip scenario, if the decay dark energy evolution measurements continue to point toward phantom dark energy, would actually mean for the universe's specific future. Into what the specific cosmological Hawking radiation of the de Sitter horizon implies for the specific information content of the universe's future. And into something I find genuinely extraordinary, the specific connection between the specific vacuum stability question and the specific hierarchy problem of particle physics, and why the specific metastability of the electroweak vacuum may be telling us something specific about the specific reason the Higgs mass has the specific value it does. The void is disappearing in specific, technically grounded, observationally motivated ways that are more interesting, more precise, and more scientifically consequential than any dramatic framing suggests. So we'd arrived at this place where the void is disappearing, points at three specific, distinct, scientifically grounded phenomena: the specific metastability of the electroweak vacuum, the Higgs field calculation showing the current vacuum may be a local rather than global minimum of the potential, with a specific tunneling lifetime of approximately 10,400 years. The specific cosmological Hawking radiation of the de Sitter horizon, the 2023 Radboud University result, extending Hawking's black hole evaporation calculation to the universe's cosmological horizon, giving finite evaporation timescales for all objects embedded in the expanding universe, and the specific evolution of cosmic voids measured by decay, the specific growth of underdense regions in the cosmic web whose rate depends on the specific dark energy equation of state, which decay's first-year results suggest may be evolving rather than constant. Now I want to go deeper into the specific big rip scenario, what phantom dark energy implies for the universe's specific structural future, into what the specific cosmological Hawking radiation implies for the specific information content of the far future universe, and into the specific connection between vacuum metastability and the hierarchy problem, why the specific Higgs mass value that produces metastability may not be coincidental, but may be telling us something specific about the fundamental structure of the theory. Let me start with the big rip. The specific dark energy equation of state parameter designated W is the specific ratio of dark energy pressure to dark energy density. For a cosmological constant, the specific simplest form of dark energy, consistent with Einstein's original equations, W equals exactly -1. This specific value produces the specific accelerating expansion we currently observe, and it remains constant. The dark energy density neither increases nor decreases as the universe expands. The specific decay first-year results and the specific combined analysis with Planck CMB data and the specific supernova data from the Dark Energy Survey and other programs suggest a specific preferred value of W that is evolving. The specific best fit value at the current epoch is approximately -1, but the specific best fit model has W changing with time in a specific direction toward values above -1 in the future. The specific value, W equals -1, is a specific dividing line in dark energy physics. Models with W greater than -1, the specific regime that includes a cosmological constant, and most quintessence models produce a universe that expands forever, but with a specific finite density of dark energy. Models with W less than -1, the specific phantom dark energy regime, produce a universe in which the dark energy density increases without bound as the universe expands. The specific reason phantom dark energy is called phantom involves a specific technical property. It violates the specific null energy condition, a specific inequality that most well-behaved quantum field theories satisfy. Specific phantom dark energy models require specific unusual physics-specific fields with wrong sign kinetic terms specific non-canonical quantum field theories that are theoretically problematic, though not obviously impossible. But if the Deci measurements are pointing toward an equation of state that crosses from above to below -1 as the universe evolves, what specific cosmologists call the phantom crossing, the specific long-term future of the universe, changes qualitatively from the standard cold, dark, expanding future to something more dramatic. In the specific Big Rip scenario, first calculated by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg in 2003, phantom dark energy with W permanently below -1 causes the universe to expand at an accelerating rate that increases without bound. The specific dark energy density grows as the universe expands, driving the expansion faster and faster. Eventually, at a specific finite time in the future called the Big Rip, the expansion rate becomes infinite. The universe's scale factor diverges in finite time. The specific sequence of events in the Big Rip is remarkable. At a specific time before the rip calculated from the specific W value and the specific current dark energy density, gravitationally bound structures begin to be torn apart. Galaxy clusters, which are held together by the specific gravity of dark matter halos against the general cosmological expansion, are the specific first objects to dissolve at a specific time approximately 1 billion years before the rip. Galaxies follow at a specific time approximately 1 million years before. Solar systems at a few months before. Individual stars at minutes. And eventually, in the specific final moments before the Big Rip, planets are torn apart, then atoms, then atomic nuclei, and finally, in the specific terminal event, the fabric of space-time itself is torn. The specific current Deci data does not definitely predict the Big Rip. The specific error bars on the dark energy equation of state evolution are large enough that the cosmological constant W equals -1 exactly remains within the specific confidence interval. The specific phantom regime is preferred over the cosmological constant at a statistical significance of approximately 2 to 3 sigma, not definitive, not sufficient for a discovery claim. The specific future measurements, DESI's full 5-year data set, the Euclid satellites' gravitational lensing and spectroscopic surveys, the Roman Space Telescope's supernovae program will reduce the specific uncertainty and determine whether the phantom preference persists. The void is disappearing in the specific Big Rip scenario, not gradually, but catastrophically, not through the specific quantum tunneling of vacuum decay, but through the specific classical evolution of an accelerating expansion that eventually tears apart every bound structure in the observable universe. Let me now take you to the specific cosmological Hawking radiation result and what it implies for the specific information content of the far future universe. The specific 2023 Radboud result established that cosmological Hawking radiation causes all objects embedded in the de Sitter universe to evaporate on specific finite timescales. The specific mechanism, formally identical to black hole Hawking radiation but applied to the cosmological horizon, produces specific thermal radiation at the specific de Sitter temperature. The specific de Sitter temperature is extraordinarily cold. For the specific current value of the cosmological constant corresponding to a specific dark energy density of approximately 10 - 29 grams per cubic centimeter, the specific de Sitter temperature is approximately 10 - 30 Kelvin. This is roughly 30 orders of magnitude colder than the cosmic microwave background's current 2.7 Kelvin. It is the specific coldest temperature associated with any known physical process. The specific evaporation timescales calculated by the Radboud team for various astronomical objects span an extraordinary range, but are all finite. A neutron star, a specific object with a mass of approximately 1.4 solar masses and a radius of approximately 10 kilometers evaporates through cosmological Hawking radiation on a specific timescale of approximately 1068 years. A white dwarf, a specific object with a mass comparable to the Sun but a radius comparable to Earth, evaporates on a specific timescale of approximately 1085 years. A supermassive black hole of the kind at the center of the Milky Way, 4 million solar masses, evaporates through the combined standard Hawking radiation and cosmological Hawking radiation on a specific timescale of approximately 1087 years. These specific numbers are vast numbers with exponents in the 60s to 90s, but they are finite, and their finitude carries a specific implication for the information content of the universe. We establish in the black hole information paradox conversation that information is preserved, that the quantum mechanical evolution of the universe is unitary, and that information encoded in physical systems is never destroyed. The specific island formula showed that even the apparently thermal Hawking radiation from black holes encodes specific information about infalling matter in exponentially suppressed correlations. The total information content of the universe, the specific quantum information encoded in all physical systems, is conserved, but cosmological Hawking radiation raises a specific version of the information question that has not yet been fully resolved. When a neutron star evaporates into specific thermal radiation through the cosmological Hawking mechanism, where does the specific information about the neutron star's quantum state go? Is it encoded in the specific correlations of the emitted cosmological Hawking radiation, in analogy with how black hole information is encoded in Hawking radiation correlations? Does the specific island formula, or its specific analog for de Sitter spacetime, apply to cosmological evaporation as well as to black hole evaporation? The specific theoretical status of this question is that it is actively debated. The specific extension of the island formula to de Sitter spacetime de Sitter holography is significantly less well understood than the specific ad-CFT duality that underlies the island formula in its original context. Specific researchers, including Strominger, Maldacena, Witten, and their collaborators, have been working on de Sitter holography for more than 2 decades without achieving the specific mathematical precision of the ADS-CFT duality. The specific reason de Sitter holography is harder involves a specific property of de Sitter spacetime. It has a specific finite entropy given by the specific Bekenstein-Hawking formula applied to the cosmological horizon. A finite entropy means a finite dimensional Hilbert space, which creates specific difficulties for the standard infinite dimensional quantum field theory methods used in ADS-CFT. The specific resolution of these difficulties, the specific correct quantum gravitational description of de Sitter spacetime, is one of the specific major open problems in quantum gravity. The void is disappearing in the specific sense that the specific quantum information content of the universe, currently distributed across specific stars and black holes and cosmic structures, is slowly transitioning into the specific thermal radiation of the de Sitter background. Whether this transition preserves information, whether the specific correlations of the emitted radiation encode the specific quantum information of the evaporated objects, is the specific question that the extension of the black hole information paradox resolution to de Sitter spacetime will eventually answer. Let me now take you to the specific connection between vacuum metastability and the hierarchy problem, because this connection is the most technically rich and most theoretically important aspect of the entire vacuum stability story. The hierarchy problem is the specific question of why the Higgs mass is 125 GeV rather than approximately 1018 GeV, the specific Planck mass, where quantum gravitational effects become important. In the specific quantum field theory of the Standard Model, the Higgs mass receives specific quantum corrections, specific contributions from virtual particles running in specific loop diagrams that are of order, the Planck mass squared. For the Higgs mass to be 125 GeV, these specific enormous quantum corrections must be specifically canceled by the specific bare mass term in the Lagrangian with a precision of approximately 1 part in 1030. This specific extraordinary fine-tuning, the specific requirement that a large positive and a large negative quantity cancel to produce a specific small result, is the hierarchy problem. The specific proposed solutions to the hierarchy problem include supersymmetry, which predicts specific superpartner particles whose loop contributions specifically cancel the standard model contributions, and extra dimensions which predict specific Kaluza-Klein towers of particles that modify the specific high energy behavior of the theory. Both supersymmetry and specific extra dimension models predict specific new particles at TeV energies that would be produced at the LHC. These specific new particles have not been found. The specific LHC searches for supersymmetric particles and Kaluza-Klein states have been progressively constraining, pushing the specific masses of hypothetical new particles to higher and higher values that reduce their naturalness, making the specific fine-tuning required less natural rather than more. The specific connection to vacuum stability involves a specific theoretical observation. In the specific standard model, without any beyond standard model physics, the specific fine-tuning of the Higgs mass required by the hierarchy problem happens to produce a specific Higgs mass, 125 GeV, that places the electroweak vacuum precisely in the specific metastable region, close to the specific boundary between stability and instability. This specific coincidence, the specific Higgs mass, that would result from specific natural but enormous fine-tuning happens to be the specific Higgs mass that produces metastability, has attracted specific theoretical attention. The specific, most discussed interpretation of this coincidence involves the specific anthropic principle in its most conservative form. If the universe contains specific many regions in the inflationary multiverse we discussed, with specific different values of the Higgs mass resulting from specific different realizations of the specific Higgs potential, then only specific regions with Higgs masses in specific ranges, compatible with atomic chemistry and the formation of complex structures, can support observers. The specific Higgs mass in our observable region would then be explained by specific selection. We observe a specific Higgs mass compatible with our existence. But the specific metastability is a specific additional constraint within this anthropic reasoning. A Higgs mass much larger than 125 GeV would not just change the specific vacuum stability, it would change the specific chemistry of atoms and molecules in ways potentially incompatible with complex chemistry and life. The specific Higgs mass near 125 GeV in the specific metastable regime may be the specific sweet spot that allows both atomic chemistry compatible with life and a vacuum that is sufficiently stable for life to develop over billions of years. This is specific theoretical reasoning, not established science. But it connects the specific vacuum metastability measurement, the specific Higgs mass and top quark mass that determine the specific regime, to the specific deepest questions about why the specific fundamental constants of nature have the specific values they do. Let me now tell you about the specific future experimental program that will most directly test the vacuum stability question and why improving the specific top quark mass measurement is the single most important experimental priority. For this specific question, the specific sensitivity of the vacuum stability conclusion to the top quark mass, the specific fourth power dependence that makes a 1 GeV change in the top mass, shift the specific stability regime boundary by a comparable amount to the specific Higgs mass uncertainty, makes the specific top mass measurement the single most important experimental input for the vacuum stability calculation. The specific current top quark mass measurements from the Tevatron and LHC experiments give values of approximately 172.5 to 173.5 GeV, depending on the specific measurement method and specific theoretical interpretation. The specific uncertainty in converting the specific experimentally measured mass parameter, the specific Monte Carlo mass, to the specific theoretically defined pole mass or MS bar mass used in the specific renormalization. Group calculations is a source of specific systematic uncertainty that limits the precision of the vacuum stability conclusion. The specific planned future circular collider FCC at CERN would operate as both a specific electron-positron collider, FCCE, and a specific proton-proton collider in its specific electron-positron phase. The FCCEE would operate at a specific center of mass energy near the specific top quark pair production threshold, approximately 350 GeV, with specific extraordinarily high luminosity. This specific threshold scan would measure the specific top quark mass with a specific precision of approximately 20 MeV, 10 times more precise than the specific current best measurements. A specific 20 MeV precision on the top quark mass would decisively determine whether the electroweak vacuum is in the specific stable, metastable, or unstable regime, eliminating the specific current theoretical ambiguity that allows all three possibilities within the measurement uncertainties. If the FCCE measurement places the top quark mass in the specific range that gives an absolutely stable vacuum, the specific conclusion would be that the current electroweak vacuum is the specific true minimum of the Higgs potential, that there's no specific deeper minimum, no specific vacuum decay, no specific threat to the current state of physics, even on astronomically long timescales. If the FCCE measurement confirms the specific metastable regime, and particularly if it places the vacuum deep in the metastable region rather than near the boundary, the specific conclusion would be more dramatic. The specific electroweak vacuum is metastable. The specific true vacuum is at a different specific field value with different specific physics. The specific tunneling lifetime is extremely long, and the specific question of what physics exists at the specific high energy scale of the metastable vacuum becomes a specific urgent priority for theoretical investigation. Let me now address something that I think is genuinely important for how we should interpret the space is slowly dying, framing the specific question of what dying means for the quantum vacuum and whether the specific vocabulary of death and disappearance captures the right intuition. The specific quantum vacuum does not die in any sense analogous to biological death. It does not cease to exist. The specific Schrödinger equation is unitary, information is conserved, and the specific quantum state of the universe evolves deterministically forward according to specific physical laws that do not include the concept of cessation. What the specific vacuum might do over the specific 400-year time scale of the electroweak vacuum's specific calculated tunneling time is undergo a specific transition. The specific Higgs field, through a specific quantum tunneling event at a specific location in space, might shift from its specific current vacuum expectation value to its specific true minimum value. The specific bubble of true vacuum would expand, and the specific physics inside it would be different from the specific physics we know. The specific inside of the bubble would not be empty or dead. It would have specific physics. specific quantum fields, specific energy, just different specific physics than the specific physics that allows atoms, molecules, chemistry, and biology as we know them. Whether the specific physics of the true vacuum would allow any form of complexity is not known. The specific properties of the true vacuum depend on the specific details of the Higgs potential at energies we have not directly probed. The specific cosmological Hawking evaporation is similarly not a death but a specific transformation. The specific information encoded in a specific neutron star does not vanish when the star evaporates through cosmological Hawking radiation. It is encoded according to the specific information preservation principle that the island formula establishes in the specific correlations of the emitted thermal radiation. The specific neutron star's specific quantum information is redistributed, not destroyed. But this specific transformation, the specific redistribution of all information from specific organized structures into specific diffuse thermal radiation over specific astronomical timescales is the specific sense in which space is dying, not ceasing, not ending, losing the specific organization, the specific structure, the specific complexity that current physical processes maintain, transitioning over specific incomprehensible timescales from the specific rich, structured, complex universe we inhabit to a specific featureless thermal equilibrium from which no further complexity can emerge. This is the specific death that thermodynamics has always promised, the specific heat death of the universe. The specific new contributions from cosmological Hawking radiation and vacuum metastability are specific additional mechanisms, specific additional timescales within this specific broader thermodynamic story. The vacuum is slowly dying not in isolation, but as part of the specific thermodynamic evolution of the entire universe towards specific maximum entropy equilibrium. Let me now tell you about the specific, recent, theoretical development that has made the specific cosmic future more nuanced than the simple heat-death picture, the specific role of quantum fluctuations in the far future de Sitter universe. In a specific de Sitter universe, a universe dominated by a specific positive cosmological constant, the specific thermal radiation from the cosmological horizon produces a specific thermal bath at the specific de Sitter temperature. In thermodynamic equilibrium, this specific thermal bath would fill the universe with specific photons and other particles at the specific de Sitter temperature, approximately 10 - 30 Kelvin. But the specific de Sitter thermal bath is not truly in equilibrium in the specific sense of classical thermodynamics. Because the specific de Sitter universe is expanding, the specific thermal bath is continuously being diluted by the expansion and continuously being replenished by the specific cosmological Hawking radiation. The specific balance between these two processes defines the specific de Sitter equilibrium state. In this specific de Sitter equilibrium, something specific and interesting happens on astronomically long timescales, something called Boltzmann brane fluctuations. In any specific thermal system at non-zero temperature, specific random fluctuations can spontaneously produce specific ordered structures. The specific probability of any specific fluctuation is determined by the specific Boltzmann factor exponentially suppressed by the specific entropy of the fluctuation compared to the specific thermal background. For most specific ordered structures, a specific functioning brane, a specific ordered crystal, a specific complex molecule, the specific Boltzmann factor is extraordinarily small. But in a specific eternal de Sitter universe, waiting long enough, even the specific most improbable fluctuations occur with probability approaching 1. The specific Boltzmann brane is a specific thought experiment, a specific self-aware observer spontaneously fluctuating out of the specific thermal bath of the de Sitter universe, complete with specific false memories of a history that never occurred. The specific rate of Boltzmann brain production in the specific far future de Sitter universe, while astronomically slow, is finite and positive. Over specific long enough timescales, much longer than the specific evaporation times of all current astronomical objects, the specific de Sitter universe produces more Boltzmann brains than it contained evolved observers during its specific structured epoch. This specific Boltzmann brain problem is not just a philosophical curiosity. It is a specific problem for any cosmological theory that predicts a specific eternal de Sitter future, because a specific cosmological theory in which most observers are Boltzmann brains with specific false memories makes specific predictions that conflict with our specific actual observations. The specific resolution of the Boltzmann brain problem, whether through the specific eventual vacuum decay of the de Sitter vacuum, through the specific recollapse of the universe, or through some other specific mechanism, is a specific theoretical priority. The specific vacuum decay that the metastability calculation predicts is, in this specific sense, a potential resolution of the Boltzmann brain problem. If the specific electroweak vacuum eventually decays, even after the specific 400-year tunneling time, the specific de Sitter phase ends and the specific Boltzmann brain production ends with it, the specific number of Boltzmann brains produced before the specific vacuum decay is finite, and with specific appropriate anthropic reasoning, the specific ratio of evolved observers to Boltzmann brains can be made consistent with our specific observations. The void is disappearing, and its specific disappearance, paradoxically, may be what saves the specific coherent structure of the universe's far future from being overwhelmed by specific random thermal fluctuations. Let me close this second part with the most important and most honest framing for the entire space is slowly dying story, what it means to understand the specific long-term fate of the universe at the specific level of precision that current theoretical physics allows. The specific calculations we've been discussing, the specific electroweak vacuum lifetime, the specific cosmological Hawking evaporation timescales, the specific Big Rip scenario if DESI's dark energy evolution measurements continue in their specific current direction, are not science fiction. They are the specific outputs of specific, well-developed theoretical frameworks applied to specific, empirically measured parameters. They are as real as the specific calculation that tells us the sun will exhaust its hydrogen fuel in approximately 5 billion years, or the specific calculation that tells us the Andromeda galaxy will merge with the Milky Way in approximately 4.5 billion years. What makes the specific long-term future calculations different is the specific exponential timescales involved, numbers with exponents in the hundreds that make direct verification impossible and that require specific theoretical extrapolation far beyond any observable. The specific reliability of these calculations depends on the specific stability of the physical laws over specific extraordinary timescales, and the specific assumption that the specific theoretical frameworks, quantum field theory, general relativity, their specific combination remain valid in regimes we cannot directly test. But within these specific appropriate caveats, the specific long-term fate calculations are the specific best answer physics can currently give to the specific question of what happens to the universe in the far future. And the specific answer involving the specific cosmological Hawking evaporation of all structures, the specific possible vacuum decay of the electroweak vacuum, the specific possible Big Rip if phantom dark energy dominates, is a specific scientifically grounded picture of a universe that is not static, not eternal in its current form, and not simply continuing the specific current pattern of star formation and galaxy evolution indefinitely. In part 3, I want to bring everything together into the complete picture of what these specific long-term cosmic futures mean for the deepest questions about the universe, into what it means to live in a universe whose specific vacuum state may be metastable, whose specific cosmological horizon is slowly evaporating everything, and whose specific dark energy may be evolving toward a specific end state dramatically different from the specific cold, dark, eternal expansion that the cosmological constant would produce, and into what I think is the most profound and most personally significant implication of the entire story, not the specific end of the universe, but what understanding these specific far future scenarios tells us about the specific present moment we inhabit. The void is disappearing on specific timescales that dwarf the current age of the universe by factors of 10, 390. And understanding why and what it means is one of the most extraordinary things that contemporary physics can show us about the specific universe we live in. So we'd arrived at this place where the void is disappearing, points at 3 specific, distinct, scientifically grounded phenomena: the specific metastability of the electroweak vacuum with its calculated tunneling lifetime of 10,400 years, the specific cosmological Hawking radiation from the de Sitter horizon that gives finite evaporation timescales to all objects in the universe, and the specific evolution of cosmic voids and dark energy measured by Deci, whose specific equation of state may be evolving toward phantom dark energy and potentially the Big Rip, where the specific Boltzmann brain problem, the specific overproduction of random thermal observers in an eternal de Sitter universe, makes the specific vacuum decay not just a cosmological curiosity, but a specific theoretical necessity for a universe whose far future is dominated by coherent, evolved observers rather than random fluctuations, and where the specific future circular collider's top quark mass measurement at 20 MeV precision will decisively determine whether the specific electroweak vacuum is stable, metastable, or unstable. Now, I want to bring it all the way home into what these specific long-term cosmic futures mean for the deepest questions about the universe's nature, into the specific personal significance of living in a moment when these far future scenarios are calculable rather than merely speculative, and into what I think is the most profound implication of the entire story, not the specific end of the universe, but what understanding these specific scenarios tells us about the specific present moment we inhabit and what it means. Let me start with the question of how to think about futures so remote they are incomprehensible. The specific numbers involved in the long-term fate of the universe are not just large, they are specifically, qualitatively incomprehensible in a way that the large numbers of everyday experience are not. The age of the universe, 13.8 billion years, is a large number by human standards, but it is a number we can situate. We can trace cosmic history from the Big Bang, through the formation of the first stars, through the evolution of galaxies, through the formation of the solar system, through the evolution of life, through the emergence of civilization. The 13.8 billion year timeline, however vast, has specific events we can identify and a narrative we can follow. The specific evaporation time of a stellar mass black hole through standard Hawking radiation, approximately 1067 years, is already incomprehensible in a different way. It is not just large, it is large in a way that makes every significant event in the history of the observable universe, every galaxy merger, every supernova, every planetary system formation, shrink to a specific negligible instant compared to the evaporation timescale. The 1067 years makes 13.8 billion years look like a nanosecond in comparison, and the specific electroweak vacuum lifetime of 10,400 years, the specific calculated tunneling time for the specific quantum fluctuation that would initiate vacuum decay is incomprehensible even by the standards of black hole evaporation. It makes the black hole evaporation timescale look like a nanosecond. It makes every physical process that will have occurred between now and the last black hole's evaporation shrink to a negligible instant compared to the vacuum lifetime. These numbers are not just numbers. They are specific signals from the mathematics of quantum field theory about the specific structure of the vacuum we inhabit, the specific energy barrier separating our specific current state from the specific true minimum of the Higgs potential. They are as real as any other output of the specific theoretical framework, as real as the specific calculation that predicted the Higgs boson mass in terms of specific quantum corrections before the LHC measured it. And their specific incomprehensibility is itself meaningful. It tells us something specific about the specific stability of the universe we inhabit. Not that it is permanent, not that it is forever, but that it is specifically stable for timescales so large that the entire history of complexity and life and civilization and future civilization represents, on this scale, not even the beginning of a beginning. Let me now tell you about the specific relationship between the specific long-term fate calculations and the specific question that has been implicit in this entire series, the question of whether the universe has a purpose, a direction, a meaning beyond the specific physical processes that constitute its evolution. The specific answer that the physics gives is clear and specific. The universe does not have a purpose in any intentional sense. The specific physical processes, the specific gravitational collapse of density fluctuations into galaxies, the specific nuclear fusion that powers stars, the specific chemical reactions that constitute life, the specific neural processes that constitute consciousness are the specific consequences of specific physical laws operating on specific initial conditions. They are not directed toward any goal. They do not have a specific terminus they are trying to reach. But the specific physics is not nihilistic in any deep sense. The specific laws of thermodynamics, the specific second law that entropy increases, the specific arrow of time that points from low entropy past to high entropy future, do give the universe a specific direction. Not a purpose, but a direction. From specific order to specific disorder. From specific complexity to specific simplicity. From specific structure to specific equilibrium. And within this specific directional evolution, the specific arrow from the specific low entropy Big Bang to the specific high entropy far future, a specific window exists. The specific window within which specific organized structures can persist, within which specific stars can burn and specific planets can form and specific chemistry can operate and specific biology can evolve and specific consciousness can arise. We are in that window, specifically, precisely, at a specific moment in the specific cosmic timeline when the specific conditions for complexity are optimal. The universe is old enough that specific heavy elements have been synthesized in specific stellar furnaces and dispersed through specific supernovae into specific molecular clouds from which specific planets like Earth can form. But not so old that the specific last stars have burned out and the specific last chemical energy sources have been exhausted. We are in the specific golden window of cosmic complexity. The void is disappearing on specific timescales that dwarf the specific current age of the universe by factors of 10^390. And this specific disappearance, understood correctly, does not diminish the specific present moment. It contextualizes it. It places it in the specific cosmic timeline with the specific precision that only the specific long-term fate calculations can provide. Let me now tell you about something that I think is the most important and most underappreciated consequence of the specific vacuum stability calculation, the specific constraint it places on physics beyond the Standard Model. We've established that the specific Higgs mass of 125.1 GeV places the electroweak vacuum in the specific metastable regime. We've established that specific beyond Standard Model theories, specific supersymmetric extensions, specific additional Higgs doublets would modify the specific running of the Higgs quartic coupling and potentially shift the specific stability regime. The specific constraint is this: any beyond Standard Model physics that generates additional positive contributions to the Higgs quartic coupling at high energies, making the coupling more positive, would shift the vacuum towards stability. Any beyond Standard Model physics that generates additional negative contributions, making the coupling more negative, would shift it toward instability. The specific measurement of the Higgs mass, combined with the specific measurement of the top quark mass, gives a specific value for the Higgs quartic couplings running that places it in the specific metastable regime. Any specific new physics that would have been discovered at the LHC, any specific supersymmetric partners, any specific Kaluza-Klein states would have modified this specific running and potentially shifted the regime. The specific non-discovery of beyond Standard Model particles at the LHC is therefore not just a specific absence of positive evidence for new physics. It is a specific positive constraint on the vacuum stability. It tells us that whatever beyond Standard Model physics exists must be at specific, sufficiently high energies that it has not yet modified the specific running enough to shift the vacuum into the specific stable or unstable regime at currently accessible energies. This specific constraint is a specific new kind of experimental input to the theory space of beyond Standard Model physics. Not we found this particle a specific direct positive signal, but we are in this specific vacuum stability regime, and any new physics must be consistent with this regime, a specific indirect constraint that rules out specific theories and favors others. The specific theories most consistent with the specific metastability finding and with the specific LHC non-discoveries are theories in which new physics exists at a specific high energy scale, much higher than the LHC's specific 14 TeV reach. Theories in which the specific hierarchy problem is solved not by specific new particles near the electroweak scale, but by specific high-energy mechanisms, perhaps related to the specific string landscape, perhaps to specific quantum gravity effects at or near the specific scale of the metastable vacuum's second minimum. The void is disappearing, and the specific physics of its disappearance is constraining the specific structure of the theory that underlies it. Let me now address the specific question that I think is most personally relevant for anyone trying to understand what the cosmic future means. The question of whether these specific far future scenarios should affect how we live and think and value the specific present moment. The specific answer is yes, but not in the dramatic way the headlines suggest. The specific knowledge that the electroweak vacuum has a specific calculated lifetime of 10,400 years does not provide any practical information for any decision on any human or civilizational time scale. The specific probability of vacuum decay in the next billion years, let alone the next billion millennia, is so specific and so small that it is less relevant to any practical question than the specific probability of the sun spontaneously becoming a black hole before its natural main sequence lifetime ends. The specific knowledge that cosmological Hawking radiation will evaporate all stellar objects on specific timescales of 1067 to 1085 years is equally irrelevant to any practical planning on any timescale. Relevant to human civilization, human biology, or any conceivable successor civilization that might exist within the next several billion years while the sun continues burning and habitable planets continue to exist. But the specific conceptual knowledge, the specific understanding of what the long-term cosmic future looks like is valuable in a different and more profound sense. It places the present moment in the specific cosmic context that is its true context. We are not in a static universe. We are not in an eternal universe. We are in a specific, finite, evolving universe whose specific current state, full of specific burning stars, specific living planets, specific evolving complexity, is a specific temporary condition that will not persist indefinitely. The specific finiteness of the universe's structured epoch is not a source of despair. It is a specific clarification of value. The specific ordered, structured, complex universe we inhabit, in which stars burn and planets form and chemistry operates and consciousness exists, is specific, contingent, and temporary. Its specific temporary character does not diminish its specific value. It specifies it. Let me now tell you about what I find most genuinely extraordinary about the specific vacuum stability story, the specific fact that we can calculate the specific lifetime of the universe's vacuum state at all. The specific electroweak vacuum lifetime of 400 years was calculated by specific physicists using specific equations derived from specific experimental measurements using specific mathematical techniques developed over specific decades of theoretical work. The specific input parameters, the specific Higgs mass measured at the LHC, the specific top quark mass measured at the Tevatron and LHC, the specific strong coupling constant measured at multiple energies are specific numbers obtained by specific experiments using specific detectors built by specific people. The specific calculation using the specific renormalization group equations and the specific 1-loop, 2-loop, and 3-loop corrections to the Higgs quartic coupling is a specific, reproducible, peer-reviewed calculation that any qualified theoretical physicist can perform and verify. We know the specific lifetime of the vacuum state of the universe. Not precisely the specific uncertainty in the top quark mass creates a specific uncertainty in the specific stability regime that the FCCE measurement will reduce, but approximately, specifically, within specific error bars that are being progressively reduced by specific experimental programs. This is extraordinary. Not in the sense of being mysterious or incomprehensible. The specific calculation is standard quantum field theory, accessible to any graduate student in theoretical physics. Extraordinary in the specific sense that human beings, using specific instruments and specific mathematics, have determined specific properties of the specific quantum state of the universe on specific timescales 10, 300, and 90 times longer than the current age of the universe. We cannot observe the specific future. We cannot wait 10, 400 years and verify whether the specific vacuum decays. But we can calculate specifically, quantitatively, with specific error bars that specific future experiments will reduce what the specific physics of the current vacuum state implies about its specific long-term stability. This is the specific kind of knowledge that physics provides that no other human intellectual enterprise can approach. Not observation of what will happen, specific quantitative calculation of what must happen given the specific physical laws and the specific current state, extrapolated forward through specific, well-understood mathematics to specific, far future conclusions. Let me now bring together the complete picture: the specific electroweak vacuum metastability, the specific cosmological Hawking radiation, the specific Desi dark energy evolution, the specific Big Rip scenario, the specific Boltzmann brain problem, the specific constraint on beyond standard model physics into the single most important insight that all of this collectively delivers. The universe is not in its final state. The specific quantum vacuum we inhabit, the specific state of the Higgs field with its specific vacuum expectation value of 246 GeV, the specific dark energy density with its specific equation of state, the specific thermal state of the cosmic microwave background at its specific 2.7 Kelvin is not the specific final configuration that the specific laws of physics will eventually produce. It is a specific intermediate state, a specific configuration that the universe has been in since the specific epoch of electroweak symmetry breaking in the first fractions of a second after the Big Bang, and that it will remain in for the specific incomprehensible timescale of 400 years before transitioning to a specific different configuration. The specific final configuration, if the specific vacuum eventually decays, will have specific different physics, specific different particle masses, specific different chemistry, specific different physical constants. Not the specific physics we know, but specific different physics consistent with the specific true minimum of the Higgs potential. And the specific, even longer term future, if the specific Big Rip scenario is correct, will end in a specific structural dissolution before even the specific vacuum lifetime is reached. The specific phantom dark energy tearing apart specific galaxies and then specific solar systems and then specific atoms on the specific way to the specific final singularity of the Big Rip. Or, if neither scenario is correct, if the specific electroweak vacuum is stable and the specific dark energy is a cosmological constant, the specific long-term future is the specific heat death of cosmological Hawking radiation and Boltzmann brain production in an eternal de Sitter universe. 3 specific scenarios, 3 specific far futures, all consistent with specific current measurements within specific current uncertainties. And the specific FCCE top quark mass measurement and the specific DESI full 5-year data set and the specific Euclid and Roman dark energy surveys will progressively reduce the specific uncertainties and determine which specific scenario best matches the specific universe we inhabit. The void is disappearing in one specific scenario, slowly over 400 years of specific quantum tunneling. In another, catastrophically, through the specific Big Rip of phantom dark energy in a specific finite future time. In either completely through the specific cosmological Hawking evaporation of everything embedded in the specific de Sitter universe over specific timescales of 1067 to 1085 years. And we, right now, at this specific moment, in the specific 13.8 billion year history of the universe, in the specific window of cosmic complexity, when specific stars burn and specific chemistry operates and specific consciousness exists, know this. Not perfectly, not with specific complete certainty, but specifically, quantitatively, with specific error bars that specific future experiments will reduce. Let me close with the most important and most personally significant thing that the entire space is slowly dying story tells us. Not about the specific physics of vacuum metastability or the specific dark energy equation of state or the specific cosmological Hawking radiation, but about what it means to be a conscious being in a specific universe whose specific long-term fate is calculable. The specific knowledge of the cosmic future is knowledge of context. It places the specific present moment in the specific cosmic timeline with a specific precision that only specific physical calculation can provide. It tells us that the specific window of complexity we inhabit is specific, finite, and extraordinarily rare in the specific sense that the specific far future of the universe, after the specific last stars burn out and the specific last complex structures dissolve into specific thermal equilibrium, will be vastly simpler, vastly less organized, vastly less capable of supporting the specific kinds of processes we call life and thought and experience. We are in the specific golden window, the specific epoch when the specific temperature of the universe, the specific density of the universe, the specific abundance of heavy elements in the universe, and the specific stability of the specific vacuum of the universe combine to make possible the specific rich, complex, evolving physics that allows the specific atoms in your body to be organized into the specific structures that allow you to think about the specific far future of the universe. This specific conjunction, this specific convergence of specific conditions is not permanent. The specific stars will eventually exhaust their specific hydrogen. The specific complex chemistry of living systems requires specific temperature ranges and specific energy densities that the specific far future universe will not maintain. The specific window will close, but it is open now. Specifically, the specific void is disappearing on specific timescales of 10,400 years. And while it disappears, the specific universe it constitutes is producing specific stars and specific planets and specific life and specific consciousness that can ask the specific question of when it will disappear and calculate the specific answer. This is what the specific long-term fate calculations are ultimately about. Not catastrophism, not nihilism, not the specific terror of the void's disappearance. The specific extraordinary fact that the specific physical universe we inhabit is the specific kind of universe that produces specific beings capable of calculating its own specific long-term fate, and that the specific calculated fate, however distant, however incomprehensible in its specific timescales, is the specific honest answer to the specific question, what happens next, asked on the specific longest possible timescale. The void is disappearing. And we know it, not from revelation or prophecy or intuition, from specific Higgs mass measurements at the specific LHC and specific top quark mass measurements at the specific tevatron and specific renormalization group calculations performed by specific theoretical physicists and specific dispersion measurements of specific fast radio bursts and specific baryon acoustic oscillation, measurements from specific galaxy surveys and specific dark energy equation of state, fits from specific deci-spectroscopic data, from specific science, specific quantitative, reproducible, peer-reviewed, experimentally grounded science that has taken specific human beings, specific centuries to develop, and that produces specific answers to the specific most important questions that specific consciousness can ask about the specific universe it inhabits. The specific answers are not comforting in any simple sense. The specific vacuum is metastable. The specific dark energy may be evolving toward phantom domination. The specific cosmological Hawking radiation will eventually dissolve every star and every black hole. The specific heat death awaits on specific timescales beyond any number with a humanly conceivable name. But the specific answers are real. And real answers, however unsettling, are more valuable than comfortable fictions. Because real answers are what the specific universe actually is. And understanding what the specific universe actually is in all its specific, extraordinary, temporary, thermodynamically doomed complexity is the specific, most important thing, that specific consciousness arising in the specific golden window of cosmic complexity can do with the specific time it has. The void is disappearing. We have calculated when, and in calculating when, in performing the specific measurements and specific mathematics that turn the specific question of the universe's fate from specific speculation into specific science, we have done something that the specific void, in all its specific, incomprehensible time scale of disappearance, cannot do for itself. We have understood it specifically. That is what it means to be alive in the specific universe we inhabit at the specific moment we inhabit it. Not forever, but now, and now is exactly when it matters.